All right, let's talk about something every developer runs into. That constant tug of war between building a database that's perfectly pure and one that's actually, fast. So you did everything right. You went through the whole process, you normalized your tables, you got rid of all the redundant data, you hit that textbook goal, third normal form. Everything is clean, consistent, logical, it's beautiful.
And then you run your app, and it's just sluggish. Queries are crawling, users are tapping their fingers waiting for stuff to load. So what gives? That's the frustrating gap between theory and reality, and that's the gap we are going to close today.
To really get the trade-offs, we have to first understand the absolute ideal. So let's push things a little further. If 3NF is great, what does perfect actually look like?
Well, meet Boyce-Codd Normal Form, or BCNF for short. It's basically a stricter, slightly more intense version of 3NF. The core idea is simple. For any dependency in your table, the thing doing the determining must be a full-blown candidate key. It's all about squashing even the most obscure theoretical data problems.
So you're probably thinking, okay, but when would I ever actually need this? If 3NF gets us 99% of the way there, where does it fall short? Turns out it's only in some pretty specific and, honestly, pretty rare situations.
You really only need to start thinking about BCNF when you're dealing with a table that has these very specific traits. We're talking multiple ways to uniquely identify a row, where those keys are made up of more than one column, and where those keys actually share columns. It is a very specific edge case, but if you're aiming for absolute data purity, BCNF is kind of the final boss.
But here's the big plot twist. Sometimes, that quest for perfection is the very thing that's holding you back. So now, we're going to pivot from pure theory to hard-nosed practice. We're going to talk about making a smart, strategic compromise.
And that brings us to denormalization. And yep, you are reading that correctly. This is where we deliberately break those normalization rules we work so hard to follow. It's not a mistake, it's a calculated move to add some data back in for one reason, and one reason only: speed. And this lays out the conflict perfectly. A normalized database, you get amazing data integrity. But the price you pay is performance, because you have to do a lot of table joins to get your data. A denormalized database, you get blazing fast reads because the joins are gone. The price, you open the door to data anomalies, and you have to work a little harder to keep things in sync. It is the great trade-off.
So how does this work in the real world? Well, a classic move is to add a pre-calculated field, like storing the total of an order right on the order record itself. Why? So you don't have to calculate it every single time you query it. Or you might just copy the customer's name into the orders table so you can avoid an entire join just to display their name. It's all about breaking a rule to save a join.
Okay, so we've talked about the logical structure, but whether you chose purity or a compromise, there are other ways to get more speed. Let's talk about the physical tools that make the database engine's job easier.
The number one most important tool you have for performance is the index. The analogy is perfect. It's just like the index at the back of a textbook. Instead of flipping through every single page to find a chapter on, say, denormalization, you just look it up in the index and it tells you exactly what page to go to. A database index does that for your data.
Now you've got two main flavors. A clustered index actually sorts the data physically on the disk, and because you can only sort your data one way, you can only have one of these per table. Super important rule to remember. A non-clustered index is more like the book's topic index. It's a separate list that just points back to the right page, and you can have a bunch of these. But, and this is a big but, indexes aren't free. There's a trade-off here too. As you can see, they make reading data with select queries super fast. But they make writing data with insert and update queries slower. Why? Well, every time you add a new row, the database doesn't just write to the table. It has to go and update every single index on that table too. This means you have to be smart about it. Absolutely index the columns you use in your where clauses and for your joins. It's a no-brainer, but don't bother indexing tiny tables. It's faster for the database to just scan the whole thing. And definitely don't index columns that only have a few distinct values, like a gender column. An index isn't going to help much there.
So, we've designed our tables, we've carefully added our indexes, but how do we know if the database is actually using them? For that, we need to learn how to read its mind.
Inside every modern database is something called a query optimizer. You can literally think of it as the brain of the whole system. When you give it a query, it doesn't just run it. It looks at the query, it looks at your tables and indexes, and it comes up with a few different execution plans for how to get that data. Then it picks the plan it thinks will be the fastest.
This is such a powerful idea. The optimizer has a secret plan, and if we could just see it, we could figure out exactly what's going on under the hood. So, how do we get a peek at that plan?
It's this one simple command, explain. You stick this word right in front of your query, and it tells the database, hey, don't actually run this. Just show me your work, show me the execution plan you would have used. It's like getting the secret blueprints from the optimizer.
And what you get back is essentially a step-by-step recipe. It might say, first, I'm going to use that index on the last name column to find Smith. Then I'll use that to get the row's address, go fetch the full row, and send it back. Reading this tells you if your indexes are actually being used or if the database is ignoring them and doing a slow, painful table scan instead.
Just a quick pop quiz to make sure this one sticks, because it is so important. How many clustered indexes can you have on a single table? Just one, because it physically orders the data and you can only order it one way. And that really brings us to the most important point of all. The goal here isn't to just blindly follow a bunch of rules. A great database designer understands the trade-offs, purity versus performance, reads versus writes, and makes smart, balanced decisions for what the application actually needs.
So the next time you're working on a project, ask yourself that question. Are you chasing a theoretical ideal at the cost of real-world speed? Or have you found that sweet spot? What's the right balance for your database?